Okay, everyone, thank you for joining us for today's Energy Symposium sponsored by the Energy Institute here at the University of Texas at Austin. I'm Carrie King, Research Scientist and Assistant Director at the Energy Institute. Before I formally introduce today's speaker, I will highlight the upcoming talks, which the next 2 weeks are going from fission to fusion, I think. So next week we will have a talk from Jansi Kandasamy from the Idaho National Lab. They do have a significant focus on nuclear power at that national laboratory, and she will talk about incorporating nuclear into the energy mix for low carbon electricity. Following that, February 20th, we'll have a research professor here at University of Texas, Swadish Mahajan, and he will talk about fusion and some efforts of a company that he is associated with pursuing certain fusion technology. So the next 2 weeks are all about nuclear. But today, it is my pleasure to host Kyrie Baker, who is assistant professor at the University of Colorado at Boulder. Title of her talk, Reducing Grid Emissions with a Software Upgrade. A little background on Kyrie. She has her 3 degrees, bachelor's to PhD from Carnegie Mellon in electrical and computer engineering. She worked for a few years at the National Renewable Energy Laboratory until 2017, where she has taken on her current position. And she is also a fellow of the Renewable and Sustainable Energy Institute. And she's going to talk about what she works on today, developing computationally efficient algorithms for energy storage, ranging from building level to the international transmission grids. And she has received the prestigious National Science Foundation Career Award for her work on combining power system operations and machine learning, as well as winning an ARPA-E grid optimization competition. So the abstract of her talk today, Reducing Operational Emissions in Power Grids, is conventionally centered on adoption of clean energy or low carbon technologies, improving or installing infrastructure such as the transmission grid to enable more seamless dispersion of electricity across geography, and load side effects or demand response, electrification of end uses, and these kinds of ideas. One of the topics she is interested in and we'll discuss today is how the independent system operators actually schedule and power plants. They're responsible for market clearing, determining prices, and to do this, they rely on certain engineering approximations of how the grid works. And these approximations of physical laws govern the power flow and in turn result in a suboptimal operation and scheduling of the grid. So she's going to talk about how that impacts how the grid works and how we can improve on that. So with that said, I am now going to stop talking and hand it over to Kyrie. And as always, please submit your questions via the question and answer feature of Zoom, and I will attempt to ask these and integrate them as possible in the middle of the talk. And those we cannot get to, we will hold till the end of the talk. And Kyrie has a relatively hard stop at 1:30 local here. So we will end relatively promptly at that time. And with that said, Kyrie, I now hand it to you.
Thanks, Carrie. And thanks everybody for being here. Feel free to ask questions in the Q&A as time goes on. So I represent a research group called the Griffin Lab. Griffin stands for something very long. I just wanted to use the acronym, but something related to grids and infrastructure. So today I'm going to be talking about how we can upgrade the software that runs the grid in order to reduce emissions. So everything that Carrie mentioned, installing more transmission capacity, installing more generation, doing energy efficiency, that's all well and good, but what can we do now with just a software upgrade? So just to make sure we're all on the same page, I'm going to go over how we currently optimize grids, why we haven't moved this towards a more physically realizable technique, why it's important to do that, and then I'll get a little bit into how recent advancements in machine learning and computing can help us do these things. So the first thing, how do we currently optimize grids? So when I talk about optimization, I'm talking about minimizing or maximizing some objective subject to some physical constraints. So this was actually formulated in the 30s, a long time ago. And then it goes all the way, there we go. It goes all the way back to the 30s where people used to solve this problem by hand, the economic dispatch problem, where they would match supply and demand in the most economic fashion. And then in the 1960s, this problem of what's called optimal power flow was formalized. So optimal power flow is sort of a formalization of how do we minimize generation cost in order to supply energy to consumers. This really came to a head in 1990 when deregulation began in the United States. So if you're not familiar, I think probably most of you are, but there are 7 what's called independent system operators or ISOs in the US that are highlighted in these different colored regions. And they are responsible for running these competitive wholesale electricity markets. So generally, generators and other suppliers, even things like batteries, submit supply curves. So the price it takes them to supply a certain level of megawatts at a certain time. And then energy consumers or large loads submit curves to consume that energy. So those things are sort of matched in accordance with physical relationships in the grid. So you may have heard this as security constrained economic dispatch. This is also optimal power flow. Economic dispatch was this very basic supply and demand clearing that I mentioned that was solved by hand or slide rules in the 1930s. That's where the economic dispatch comes from. It's economic because we're minimizing costs to produce the energy, and it's dispatch because the generators are being dispatched or told to produce a certain level of power. So there's a lot of different markets and there's a lot of different market products, but basically the main layout is in the day-ahead market, there's bids submitted in advance. The ISO, the independent system operator, collects all the bids and runs SCED, or security constrained economic dispatch / OPF. The solution to this optimization, and I'm not going to display the whole optimization here because it's pretty large scale and pretty complicated, is used to quote unquote clear the market. So after the market is cleared, then these assets actually get commands to produce or commands to consume or commitments to provide a certain service at a certain time. So this is kind of the status quo right now in these ISOs, in these competitive wholesale markets. So why is it hard to do this problem better? And where are the efficiencies in this problem? So to answer that question, I first need to tell you about the physics behind the OPF problem. So there's something called ACOPF. The grid here runs off of AC power, which is alternating current. It fluctuates up and down 60 cycles per second, 60 hertz. Other countries have 50 hertz, some have 40 hertz. But that basically just says how fast conventional generators are spinning and how fast inverters connecting devices like solar panels or batteries have to create waveforms. So the ACOPF is the physically accurate grid optimization problem. This includes actual physics of how the power flows throughout the grid. It models voltage and reactive power, and it's very hard to solve. People's entire careers are dedicated to solving this ACOPF problem. It's very hard. Ideally, if we were to solve the exact grid optimization problem, we would achieve peak economic efficiency, in accordance with the objective we've defined. But because this problem is so hard to solve, what grid operators actually solve is a simplification of it, the SCED problem, or what's called the DCOPF problem. So they make a bunch of simplifications, which I'll talk about in a second, in order to make a nice linear set of grid physics, which are non-physically representative. The DCOPF in its purest form ignores losses. Most ISOs add a little calculation in there to estimate losses to account for this fact. It assumes all the voltages in the grid are equal. It ignores reactive power. There's a lot of simplifications made, and magically, this still is able to roughly govern the grid. So there's a couple reasons for that. There's many layers of redundancy in the grid that help it stay stable, help the frequency stay at 60 hertz. But the point is, we want this, and we're currently using this. So what does the ACOPF problem look like? Why is it so hard to solve? Well, this is, again, extremely simple, but we're minimizing the cost of power from different generators. So PG is the active power generated from generator J. The ISO collects these bids, they aggregate them, they minimize the cost, picking the cheapest generators to run subject to power flow constraints. The true power flow constraints have sines and cosines, multiplied by other variables that are then multiplied by another variable. These constraints are really hard to optimize. If you've ever taken an optimization class or if you know anything about optimization, most solvers that solve these kind of problems take derivatives or gradients. When you take a derivative of a sine and a cosine, it becomes another sine and a cosine. So it's very hard for the solver to move in the right direction to get the minimum, roughly speaking. So these equations are hard to solve, which is why we simplify them. Now, there's a simplification in physics called a spherical cow, which is where in order to simplify the problem, you assume the cow is a sphere, and that allows you to calculate things like air resistance more simply, because now you don't have to calculate a very complicated volume. You just calculate it with respect to a sphere. So DCOPF is sort of similar. The engineering assumptions we made are, again, we assume lossless lines. So connecting two buses in the power grid or two nodes where power is flowing from. Those nodes have a line, a transmission line connecting them. That transmission line has an impedance Z. We first assume that the resistance of that line is equal to 0. We only assume that the imaginary portion exists of the line. And yes, AC power has imaginary values. That's also part of what makes it hard. We assume there's no reactive power. And actually, this just comes from the other assumptions, but this Q variable, which is another byproduct of AC power. When you have an alternating current, it produces a magnetic field. Sort of side effect of that is you also have this other form of power that oscillates back and forth between capacitors and inductors in the grid. That's called reactive power. That's 0. And reactive power is actually very important for voltage control. So there's a lot of problems in DCOPF with voltage. We assume that there's a small voltage angle difference between the bus. So voltage here is a complex quantity, which means it has a magnitude and an angle. Any AC waveform can be described as the magnitude of the waveform, or basically how tall it is, and the phase shift of the waveform. It's a little hard to explain if you've never seen it or taken a circuits class, but basically there's a magnitude and an angle or a phase shift that describes voltage. We assume that this difference between those angles is very, very close to 0. And what that allows us to do is if you have a sine of an angle that's close to 0, that can be approximated as the angle itself. And if you have a cosine of an angle that's close to 0, that can be approximated as 1. And this kind of can be seen, maybe I'll just draw it for you. So if we zoom in to, let's do cosine first. So cosine very close to 0. Remember, cosine starts at 1. In this region, cosine basically just looks like a 1. So for very small angles, we assume this whole quantity is 1. Sine, on the other hand, starts at 0. It's a sine wave. It looks like this. If we zoom into that region where sine is very close to 0, that approximately looks like a line. It looks like y equals x. So we can approximate this whole thing as the argument of the sine or the theta. So we've gotten rid of the sines, we've gotten rid of the cosines. We've assumed all the voltage magnitudes are 1. So we've gotten rid of that complicated variable multiplication. And then we finally get this DC power flow equation, which is nice and linear. The only variables in this equation are the power generation and these angle variables that come from the sine here. So there's different ways to formulate this problem. What the ISOs use inside the software is a different formulation, but this one is it's equivalent. This one is just the nice one that is derived directly from the AC power flow equations. So we have these now, these nice linear equations. So what does this get us, and why do ISOs make all these simplifications? I mean, yes, the equations are nicer, but it has a very specific property, and that's called convexity. So it's not necessarily hard to solve a nonlinear problem. It's hard to solve a non-convex problem. Non-convex means that there can exist multiple points that are optimal, or that a solver might think are optimal. So here I just show a one-dimensional optimization problem where we're trying to minimize some function x as a function of the optimization variables x. So we're trying to determine the best x that minimizes this function. In our case, this is the best power generation that minimizes the cost. This pink line is non-convex because it has 2 points where the derivative is equal to 0. And like I told you before, these problems are solved by taking derivatives, taking gradients, and seeing where they're equal to zero, basically. It's more complicated than that, but you can think of it as that. So the hard part here with non-convex functions is how do we know that we've found the actual minimum? There could be, let's say we get stuck in this one when we could have gotten a solution that's 20% cheaper. The convex function, on the other hand, this one, the DCOPF, only has one minimum. And so we know that if we've solved that problem, we found the best solution that minimizes the objective. And this is really, really nice. It gives nice properties for prices. It gives very stable behavior for the DCOPF. And we want stable behavior when we solve an optimization problem that's operating physical assets. But ideally, this one has a cheaper cost than this one. It's lower down on the y-axis. So it would be really nice if we could come up with a way to solve for the better operating point in the grid. So as I mentioned, thousands of people have looked at this problem. There's a lot of clever things people have done. They've taken the original optimization, they've broke it up into pieces, and they solve the pieces in an efficient way. They've done something called convexification, which is where they take the non-convex function and they represent it with a convex version. You can do a lot of these different things. At the core of it, it's still solving optimization problems. And to my knowledge, none of these have been readily adopted in ISOs yet. So we're still working on this problem as researchers. So again, is it important? The grid is kind of working, most of the time. How much money could we save? Could we save carbon? So these are questions that we need to seriously consider when we think about transitioning from the linear model to the non-convex model. Is DCOPF that bad? So it does result in physically infeasible solutions. If you ignore losses and you ignore voltage and you ignore reactive power, this makes sense. And even if you include a model for losses, you can read my paper on it and you can see that it's still not physically feasible, which results in less precise economic signals. Okay, fair. Maybe we lose, a couple $100 million a year across the US, but is that a big deal? Well, as I'll also show you, some of our recent work shows that actually it's not just bad from a cost perspective, but it actually increases carbon emissions. So what do people do in practice? What do grid operators do? Well, basically they run a DCOPF to clear the market to determine prices because it's this nice linear thing. Then they run a post-processing procedure to adjust the reactive power output, adjust the voltages, make sure every actual line flows are within limits. And this is called an AC power flow. So you'll notice the O is not in there. It's not an optimal power flow anymore. So there's just a post-processing procedure where they take the generator dispatch and they adjust some of them to account for physical realities of the grid. So, I'm not the only one that thinks moving towards the high fidelity model is important. In a FERC report in 2006, they said that basically, improved modeling of system constraints such as voltage and stability constraints would result in more precise dispatches and better market signals. But the switch to AC-based software would increase the time to run a single scenario from minutes to over an hour, making the use of ACOPF impractical. So obviously in 2006, computing was a lot worse than it is now, but the ACOPF is still a very hard problem. Even with what we have now, it's hard for ISOs to run this across a whole, PJM interconnection. So there's a recent competition that started in 2019 that myself and many others competed in called the ARPA Grid Optimization Competition. DOE invested millions of dollars into having people compete to develop software to solve ACOPF in a realistic way that could be used by ISOs. And there were some really good software that came out of this, really good algorithms that came out of this. I hope eventually some of those will get to be used in actual grids to basically help close this optimality gap. Okay, so the whole talk title is based off of emissions. I have this catchy title. So what does this have to do with emissions? So I presented this before and somebody said, I don't care about grid operators saving $50 million. I care about climate change. So we ran an analysis looking at the impact on emissions when we run the DCOPF with that AC power flow post-processing to make sure it's physically realizable, versus if we were to have run the AC problem directly. So this was on a very small 118 bus system. So that's probably the size of, like, I don't know, a small state or half of a state or something. What we found was that in terms of increasing emissions, due to the inefficiencies within the DCOPF, there was 28% more emissions than if we were to directly have solved the true physical problem. Surprisingly, there wasn't that much increase in cost, around 1.4% increase in cost, which there have been people, Tom Overby included, who have done different analyses comparing the AC model with the simplified model and shown roughly the same ballpark of economic inefficiencies. But so far, there hasn't been a comparison of emissions. So these emissions are significant when you add them up. We're working on this right now. That was a small 118 bus system. We're coming up with that emissions number and that cost number for ERCOT. So basically using a synthetic representative model of the ERCOT system, how many emissions and how many millions of dollars could we save if we shifted from the way that things operate now to the full high fidelity model? So where do these inefficiencies come from? So the objective function in the OPF problem minimizes generation cost. This does not necessarily minimize emissions directly. So how is the DCOPF increasing emissions? Well, if you're familiar with the way that certain generator types bid into these markets, generally zero carbon or renewable sources bid close to zero. They're selected regardless. They're mostly limited by transmission constraints and some voltage constraints. Then we have things like nuclear, which have to run, so they generally bid lower, so they're insured to run. They can't turn on and off within a few hours. They can ramp up and down, but they can't turn on and off. And then the more expensive sources like gas and diesel and oil, if you're in an area that has oil plants, usually get the highest price. So DCOPF and ACOPF basically will all dispatch the renewable sources. But the difference comes when you have a mismatch between where the market cleared at and the actual physical realization. And in order to make up that mismatch in the real-time market, you need to rely on fast ramping peaker plants. So in the previous study, we assumed that the plants that made up that difference were gas turbines. You could also have batteries do it. So that's another, that may have reduced the emissions number. But regardless, even if it's a 10% increase in emissions, that's still a lot. So that's kind of where the inefficiencies come from. Now, in defense of DCOPF, I didn't talk about how prices are derived from these OPF models. It's actually a really cool mathematical phenomenon. It's derived directly from the optimization problem itself. When you have a non-convex optimization, the prices are not trivial. They have odd behavior. It's not as well behaved as the DCOPF. So you can imagine a market where you have prices fluctuating like crazy and it's unstable. That's not really a nice economic situation. It's easy to come up with layman's interpretations of power and prices. You can train people by basically saying, the price is a function of this cost plus congestion cost plus losses, which is a nice, easy to interpret concept, even though in reality, it's not as simple as that. You can approximate those losses. So even if we ignore the voltage magnitudes and the reactive power, at least we can incorporate losses. So that's what most ISOs currently do. And DCOPF from a mathematical point of view is nice because it's easier to write proofs for academics. So it's a nice linear problem, which lends itself to guarantees and guaranteeing when prices behave a certain way and guaranteeing when generators behave a certain way. So it has more stability in general. So I'm not anti-DCOPF, just to make that clear. So solving this ACOPF problem, how can we do it? It's very, very hard. And the sort of bottom line that I thought about was solving a large scale optimization for like 7,000 buses, for example, for Texas, or 30,000 buses for PJM, or however many PJM has. That's really hard. Is there any way that we can just bypass solving an optimization to run this grid altogether? Can we operate grids in an optimal way without solving an optimization? So the idea here is, let's take our time offline, run hundreds of thousands of ACOPFs. We can take as many, we could take 5 hours to solve one if we needed to. We could find the global optimal solution. We can run all sorts of different operating conditions. And then what we do is we train a model using all that data to learn a mapping between system state and optimal generator dispatch. So neural networks, to make a prediction, you basically just do a bunch of function evaluations, which is really fast. It's not like solving an optimization where you're taking gradients and you're inverting matrices and you're doing really, really hard things. So can we just have a 1-second ACOPF prediction? Now, you may have a lot of distrust for AI, and with good reason. I asked ChatGPT 2 days ago, how many buses are in PJM? And it responded, PJM does not manage buses. It oversees the electricity grid. Oh, thank you very much, ChatGPT. That's very insightful. And then somebody else asked, how many conductors, which is another word for metal conductors, transmission lines, distribution lines. PJM does not directly employ conductors in the sense of individuals who manage the operations of trains. So this is pretty bad. Buses is a very common term used in ISOs. So you would have think the context clue of including an ISO name in the term bus would have indicated that we're talking about electrical buses. But this confidence in AI is problematic. So how can we make system operators use this kind of AI-assisted solution? Well, right now, here's the status quo. We run SCED, or DCOPF. That gives us a suboptimal and physically infeasible solution. We post-process it in order to get it to be feasible, and that's what we currently have. Let's replace this box with another model. This one's already physically unrealizable. So this one may be 2, but it's going to be at least closer, and it's going to be a little bit cheaper and lower carbon. So we have a model that predicts ACOPF solutions. We still run the same post-processing to make sure it's physically feasible. But this one is a lot closer to the true optimal than this one. So the idea here is, by replacing this box with another model that predicts OPF solution, we can get a lower carbon, lower cost solution. So how much faster is it? So the layout is this. You input the system state, which in this case is just the demand across the whole network. The neural network, which has been trained on thousands of examples, mapping system state to optimal solution, gives you the optimal solution, and you post-process it just like ISOs do now with an AC power flow solver. This part takes milliseconds. This part takes a couple seconds. So overall, the speed up we get is, on average, 12 times to 14 times faster. So you can kind of imagine that this gives operators a little bit more confidence that they're going to be able to run a 5-minute market if we can make predictions in a few seconds of ACOPF. Now, you may be thinking, wow, these large machine learning models like LLMs, ChatGPT, they have a non-trivial amount of energy they use to train the model. What about the emissions from that training? Okay, so this is nowhere even near the scope of an LLM. The ACOPF problem is very hard, but it is not as hard as some of these large language models. So the results I'm going to show you here, they were trained on my old 2017 MacBook Pro locally, so just on the laptop itself. I used a shallow network. So deep learning means that you have multiple hidden layers in the network. There's just one here. And instead of predicting the optimal solution directly, I trained a neural network to emulate an optimization solver. So it's basically trying to take the same derivatives, the same little baby steps as the solver does to find the optimal solution, except it does it faster because it doesn't actually have to take derivatives. It doesn't actually have to do matrix factorizations. So here's a much larger system. 1354 bus system trained locally. You input the current guess for your optimal solution. The neural network predicts the next step for a guess. It keeps iterating until it's reached something that it thinks is the optimal solution. And then you post-process that with the PowerFlow solver. So very small network, very simple training. How well did it do? So this is for the 1354 bus system. So on average, across the testing data set that I used, the error in the cost function versus the true ACOPF was around 1%. So this doesn't seem like a lot, but it does result in hundreds of millions of dollars possibly. The time that it saved me was around 20 times faster. So this neural net model achieved a feasible solution that was close to optimal in 20 times faster. But who would accept this economic inefficiency? You show this to a grid operator, you say, oh yeah, it's only 1% off, but that does result in hundreds of millions of dollars. Well, right now, if you run the current model, the DCOPF with the PowerFlow correction, it's over 2% off from the true optimal solution. So here's a gap that if this is acceptable, the 1% should certainly be acceptable. Or that's the worst error, sorry. The 1.87% is acceptable. The 1.1% should be acceptable. Now, if you're familiar with other approximations to the ACOPF, you could be like, well, there's a lot of other people who've developed approximations. Why don't we use one of these? So I ran what's called the second order cone program relaxation, and it still has a higher error than the neural network did. And it solves the neural network to solve one of these ACOPF problems. It takes a quarter of a second, again, on my laptop, versus solving the simplified problem takes 33 seconds. So if you extrapolate this up to a system that's the size of ERCOT, maybe it takes, 2 minutes to solve. Well, actually, it would still be on the order of like 1 second. So it takes a couple seconds to solve with a neural network, and it takes too long, 6 minutes to solve with these other relaxations. So the point of this is, if DCOPF is acceptable now, the neural network could be acceptable. It results in lower error, it's faster, and you still get a physically realizable solution because you're using the same post-processing technique. I just want to give a shout out to all the other works that have been done in this learning for OPF space. There's some really, really good ones in here that ensure that PowerFlow constraints are adhered to, for example, that include more network physics, a lot of them, many, many more. Okay, so let's jump ahead. Let's say we're in this magical future where grid operators have adopted my algorithm and they're solving ACOPF quickly. They're like, great, I can clear the market every 1 minute. And once we get into that time frame, we're no longer talking about PowerFlow equations. We're getting into generator dynamics. We're getting into frequency. We're getting into things that aren't modeled in the OPF problem. The PowerFlow equations are called steady state for this reason. It's like there's no weird fluctuations in frequency happening. Everything's stable, and we're assuming we're economically operating them. So right now, when there's an issue with frequency stability or voltage stability, a lot of power plants have these heuristic rules to adjust their output to stabilize frequency. They're called droop curves. So here's an example of a generator droop curve that a power plant might have. If it detects that the frequency is off from what it should be, it adjusts its active power according to this linear control rule. So this is obviously not optimal adjustments. This is just, heuristic adjustments because we're unable to solve an optimization problem every 4 seconds. So what we did is, another one of our work is, how can we ensure that these fast optimal set points produced by the neural network process don't cause frequency instabilities? So we developed what's called a physics-informed neural network that it's basically an advisory tool. You send the output of the OPF to this advisory tool, and it instantly spits back, is this going to be an unstable set point or not? So you're not basically telling the generators to change their output in a crazy way. So without going into too many details, this is a very simplified generator model. It's called the swing equations for a generator. We have this delta variable basically indicates stability, and you can see that the neural net that we developed predicts this delta variable with extremely high accuracy. So this would tell us if we're going to have an instability. And the way that this works is that the physics-informed portion of the neural net embeds the equations, the differential equations directly into the neural network. So as you perform inference or as you move from left to right, making a prediction, it attempts to satisfy these physical relationships. So here's an example of an unstable generator condition. The black dashed line is what actually happened, and then the red line is our model that predicted it. It did a very good job. There's still some error, but the key point is whether or not it's stable or unstable, and it predicted that correctly in all of these cases. So the generator model we used for this is very simplified. Generators are actually quite complicated. So we've implemented a fourth order generator model, and those results should be out soon. Okay, so I'll go through this one kind of quickly, but we talked about why it's important to move to ACOPF because it's more physically realizable, lowers cost and lowers emissions. We talked about how we can use machine learning to solve that hard ACOPF problem. And now let's talk about a couple other applications for software, not installing things, not installing grid enhancing technologies or new transmission lines or batteries, just software. Can we do something today that makes the grid more efficient and lowers emissions? So there's a concept called optimal transmission switching. And this is used, to my understanding, used more in Europe on a regular time scale than it is here, but we do use it here. We actually connect or disconnect lines dynamically in order to improve the performance of the grid. This problem's really hard to solve. Again, hundreds or thousands of papers on it. It's a mixed integer problem, which means it has normal continuous variables and it also has integer variables. So you might have a variable that can either be 0 or 1, this discrete Boolean value. That makes it really hard for optimization solvers because you can't just take a derivative when there's this discrete jump like that. So why would it be good to turn off a line? This seems very unintuitive. It's quite interesting. If you look at network problems or even in transportation problems, sometimes limiting the number of paths for cars to flow or limiting the number of paths for electrons to flow can actually force them to flow in a more efficient way. So here's a very small 3-bus example that I came up with. There's 2 generators. We would ideally want to get the most power from the cheapest generator. There's a line who hits its limit of 200 megawatts. And so we then start pulling from this generator. If we actually disconnect that line, then it can use more power from generator 1. And this would take me about 15 minutes to explain. It comes from the power flow constraints, but you cannot just tell power where to flow. You cannot tell generator 1 to flow more power this way. The power flow is going to do what the power flow wants. If it's sending 200 this way, it's going to only be able to send 100 this way. And so this is a very hard thing for people to reconcile in their brain. Why can't you just tell the generator to do that? And it's like, well, if you read out the equations, you'll see there's a violation in the constraints. So this is what grid enhancing technologies aim to do. If you change the parameters of this line, the generator could send more down there, for example. But one thing we could do today without hardware is disconnect this line. So the optimal transmission switching problem was included in the ARPA Go competition because it could be so valuable for grid operations. The basic formulation of the problem, let me see if I can maybe go through this. Okay, so we have the DCOPF constraints. Is there optimal transmission for ACOPF? Yes, there is. It's very hard because you not only have those non-convex constraints, but you also have integer variables, which makes it extremely hard. So this constraint right here is the limits on the voltage angle. These constraints are the limits on the generators. They can only produce so much. This Z variable here are integer variables. If the line is disconnected, it's a 0. If the line is connected, it's a 1. So let's look at what happens when it becomes 0. This is the line flow between buses N and K. If the Z becomes 0, it forces the right-hand side to become 0. It forces the left-hand side to become 0. And we get P and K has to be 0. So turning off a line forces the line flow to be 0. Conversely, if this is 1, then the line flow is allowed to be between its min and max limits. Now you could say this is great, you just add a binary variable, but then there's all these extra constraints that make the optimization even harder. These are called big M constraints. So why do we need these? So if we force Z to be 0, forcing the line flow to be 0, that line flow variable, which is defined in the power balance constraints, if that was 0, that would force the voltage angle difference to be 0 as well. We don't want that. Buses are maybe connected to like 5 other buses. If we force that angle difference to be 0, that's limiting the line flow on other lines. So we have to basically formulate this in a different way that allows that line flow variable to be non-zero when the line is shut off, allows the voltage angle variables to be non-zero. It's a little hard to think about in this limited time frame, but basically you have to add these constraints to make the problem work properly, and those constraints make the problem even harder. Why don't we include this in every single DCOPF at the 15-minute market clearing level? Well, it's really hard to solve this problem. So people have come up with heuristics for knowing which lines to turn off. And the first heuristic you may think of, if I just gave you a bunch of examples, you would notice that a lot of times the line that is congested is the one that's removed from the system. If you remove the congestion from the system, it oftentimes decreases the cost. Super counterintuitive because this line is very important. The congested lines are the ones that the system wants to use more, but counterintuitively, sometimes removing them helps. So previous work in heuristics turned off congested lines. But you can imagine, like, especially in West Texas, you got a bunch of wind, you got a bunch of transmission lines that are constantly being hit at their limit because there's not enough transmission to carry that wind out. Those lines are really important. If you disconnected them, you're not going to get the wind anywhere. So it's not enough to say that we disconnect congested lines and we improve the economics of the system. So which lines do we remove? So the key point that we figured out here is every optimization problem has what's called a feasible region. This is the region of physically realizable solutions. That's what the optimization is trying to stay in the bounds and minimize. In this feasible region, our minimum of the problem, minimizing cost, would be down here if we didn't have any constraints. Adhering to those constraints, the closest we can get to that unconstrained minimum is here. Now, if we removed this constraint right here, this line, which basically says all your solutions have to be greater than or equal to me, and this line says all your solutions have to be greater than or equal to me, this line says all your solutions have to be less than or equal to me. The intersection of all these is the feasible region. If we remove one of those, we can increase the feasible region in the direction of the true minimum. So the idea is we're going to remove the lines that increase the feasible region in the right direction. That's the main key constraint. So removing lines can result in infeasibility in general. That's part of the reason that the N-1 criteria exists, which is if a line goes out or a transformer goes out or a generator goes out, FERC says that you need to have a path for power to flow to meet all the loads. We didn't consider this criteria here, but you can add it in as a constraint in the problem. So how do we know which constraints to remove in order to make our feasible region bigger? So let's take a look at this snapshot of the power system, one of the power systems here. So right here, I guess you can't see my cursor anymore. Oh yeah, here we go. Right here, bus 49 looks really important. It's basically connected to a lot of lines, which basically means this theta 49 variable appears in a lot of constraints. So maybe if we remove one of those lines, that equates to removing a constraint from the optimization and increasing the feasible region, which basically means that I can have more options for what theta 49 can be, and the flows can flow in a potentially more efficient way. So this is the heuristic algorithm. You solve the DCOPF, the normal market clearing. If you have constraints or lines that are binding, you look at the buses which have the most lines connected to them. Then you systematically try to remove, not in real life, remove in the simulation, remove those lines that contain that highly constrained variable, resolve the DCOPF, and then you pick the one that results in the lowest system cost. So how well does this do? So we compared it to the Gurobi solver, which is probably the best mixed integer solver that exists in the world. For a small 14 bus system, we get the same result as Gurobi. For a larger 30 bus system, we get about less than half of the cost improvement. For the large 118 bus system, we got almost exactly the same cost improvement. And some networks don't benefit from you shutting off lines. So this 200 bus, there was no improvement from disconnecting lines. But this guy, the heuristic, can solve extremely fast, whereas Gurobi, even the state-of-the-art solver, if you blow it up to like a realistically sized system, it's really, really hard to solve. It might take 6 hours to solve for a 1,300 bus system, and you're not going to have 6 hours to solve it because at that point, that's no longer what the system looks like. The load has changed. So there's also diminishing returns. You might just want to pick one line to shut off before you terminate the procedure. You can see in the 30 bus, it only shut off one line, and that reduces the cost significantly, for example. Okay, I know that last part was fast, but to wrap up, suboptimal grid operations do have to do with the algorithms at heart of operating the grid. And these increase cost, but more importantly, or possibly more importantly, they also increase emissions. Using what we have today, we are already doing optimal transmission switching. We're just not doing it regularly enough. We're also using a simplified grid model. We can move to a more realistic grid model that we actually can solve with the assistance of machine learning. We have a bunch of data. We have the ability to train models efficiently. Why not use this in the loop? We can incorporate topology optimization, and we can include more dynamic constraints in the optimization, like dynamic line ratings, which are still currently underutilized. Okay, thank you. And thank you to my group that helped with all this research. And I could take, I think there's 6 questions. I don't know if you want me to read them or you want to read them.
Up to you. You can take them. I'll interject one myself here. When you use the word, I guess for both the transmission and the solving of the optimal power flow problem you mentioned, it could be more efficient. It was not clear to me if you meant only become lower cost, or if you meant could become lower cost and thermodynamically more efficient.
Sorry, lower cost is what I mean.
Yes. Okay. Very well.
Yeah, it actually, the thermodynamically efficient may not be true with the lower cost.
All right, we may have to check our thermodynamic, our second law or something there to see what's going on. But yes, if you'd like to pick, you can pick amongst the questions if you like. Otherwise, I'll try.
I'll just do them in order.
Go for it.
Is there a reason why you chose ERCOT for your optimization analyses? Are the models simpler since it's a single state optimization, or deregulated market policy reason that makes it easier for them? Okay, gotcha. So the reason is because it's easier to model. Let me go back to that one. It's really hard to come up with conclusions of emissions and cost when you have a ton of external imports and exports. Like CAISO, for example, imports 25% of their power. So it's really hard to say with a definitive reason that switching the grid model results in X% emissions, because it depends on the mix of the adjacent states. So ERCOT has less of that problem, where the tie lines are much smaller. They're DC tie lines. So you can come up with more definitive answers for the emissions and the cost.
So reason number 21 for ERCOT not to connect to the rest of the country, so that Kyrie can more easily test her algorithms.
Easier. But yeah. Okay, and the next question, please explain the big delta of emissions versus cost optimization. Okay, that's a good question. So here, you only see that there's a 1.4% increase in cost when you move to the ACOPF model. This is because the DCOPF is actually pretty good at targeting roughly the same power flows. The only issue is, which basically means that the objective function in both cases ends up being decently close. Which is also why people haven't complained too much, because it's like, it's not like a crazy difference. It's not like $1 billion a day or something. But the emissions are when you operate the system in a way that's physically infeasible, and then you're like, oh crap, I need to balance supply and demand in order to stabilize frequency. You kick on these high emitting, fast ramping plants like gas. So this could change as more batteries come online. For example, the batteries could be the ones making up this difference. But right now we're modeling them as gas. And then how good is this solution versus the ideal? E.g. a retrospective Monte Carlo. Well, I don't know if you could solve an ACOPF optimization problem with Monte Carlo. That sounds, the solution space is too big. So I don't know if you could do that, but you could use a global optimization solver and get the true answer. And that solution is quite close to the neural network solution, for example. And then how feasible is it to implement technically bidding day ahead? It should be very feasible. That's why I tried to keep it at the same sort of flow that we have now, which is you run some model, clears the market, and then you do this post-processing. The only thing I think that is the true barrier to this is non-technical. It's the fact that market participants would be crazy if they change the way that the market runs. Traders would, all the algorithms would break, like everything would be totally different in the clearing stage. But physically, I think it would be better. The next question is, what are the implications for real-time demand response? Yeah, I thought about that. Demand response is a lot harder to address here because it relies kind of on behavioral models, unless you have this people that have opted into direct control of their assets. Anytime you have humans in the loop with this, it's sort of hard to draw conclusions definitively. But I guess you could assume, that there's people who have committed and they would do what they said they would do. But this could be used for that too, basically solving optimization problems on a large scale in general, I think. And then the next question, if we turn off a line to have more optimal flow, are we still paying for that energy that was promised to be available, even if it's shut off? Well, there would still be some, I guess, capacity payments in that case for generators that, well, yeah, I'm not sure how to answer that because the idea is the operational cost would go down, but all these other payments, I'm not sure how they would be affected. But in general, the cost for everyone would go down. Could this incentivize overbuilding capacity, knowing that a new line will create a suboptimal solution and be kept off? Well, I don't know why the ISO would have any incentive to overbuild capacity other than resiliency. And there's also, regulations against things that you can't just build stuff if you don't show that it's going to result in cheaper prices for consumers and stuff like that. So I don't think so.
Well, I guess part of the clarification there is it's not that you're delivering the same amount of energy. I think the question implies that something that promised to not, it's actually delivering exactly what was needed in both cases.
True. Yeah. Supply and demand are still met. It's just the cost is lower because you're drawing power from cheaper plants or you have less losses. That's where the cost saving comes from. How will this modeling capability be built into the proposal processes for bidding out new generation or transmission capacity? That is a good question. I don't know enough about the transmission capacity expansion process from a regulatory perspective. It would be really interesting to show, depending on the algorithm, how does that affect my bid or my proposal? Yeah, so the idea is basically just from an operational perspective with our current system, shutting off lines, which just cuts costs. So I'm not saying anything about planning or new assets, but that's a whole different question. Probably for offline follow-up, would this be applicable to local energy markets on a distribution grid using transactive energy and distributed energy resources? Well, those problems are generally a lot smaller, so you don't have this issue of it's really hard to solve ACOPF across the whole PJM interconnection. If you're just doing it within a state or something, probably the existing software could do this all off the shelf, and you wouldn't have to rely on neural nets or anything. Yeah, and that also kind of gets into distribution grid optimization, which I didn't talk about here, but there's a whole, slew of opinions on that. So I'm not sure. How much of an impact does the marginal addition of non-dispatchable power generation have on DCOPF? The marginal addition of non-dispatchable power generation. It has a lot. So basically that's like, must take generation or renewables that bid in and are selected. It changes the optimal solution significantly. And basically, as more intermittent generation comes online, you're getting a lot more uncertainty in the OPF in general. So a lot of the assumptions that the OPF makes, like voltages are all equal, the angles are close together. Those assumptions are getting a little bit worse because we're getting a lot of more dynamic behavior at buses. So the farther we get from those assumptions, the worse this gets. And the more it motivates this, I would say. What is the solver used to generate optimal data for the ML models? How does this solver guarantee the true optimality? Okay, that's a good point. I kind of glazed over because I wasn't sure about the background of everybody. This one, oh, slide 20. This one, I'm just assuming that you can use the solver that you want, but right now what I used in my simulations is not one that guarantees global optimality. So there's some papers that show results on, based on your starting point for the solver, can you get the globally optimal solution for the ACOPF? And in general, you do, but there's no proof of that. So here, you would have to run some solver that guarantees global optimality. So I didn't do that. In layman's terms, what happens if the DCOPF is way, way off? Well, in general, I don't know of a situation where it has been way, way off, although there have obviously been brownouts and blackouts due to reactive power issues and due to issues with voltage stability. So that kind of, could have been better with DCOPF, but it's hard to say definitively it was due to this. Because again, this AC post-processing should fix a lot of those issues. It's mostly the economic issue and the carbon issue, I would say, that comes from this. As more renewable energy sources get connected in the grid, is it possible to incorporate them into the optimization, and how will they affect the training? Yeah, so that one is hard. This block right here, run hundreds of thousands of ACOPFs offline. That's way easier to do when you don't have to sample from renewable energy distributions. If the only uncertainty is like load and maybe generator availability, that makes this space a lot easier to sample from, and it makes it a lot easier to train the ML model. When you also have to sample from wind distributions and solar distributions and uncertainty in temperature and how that affects those generation profiles, this block takes more time and would probably result in a larger ML model. But it's possible, I would say. And then the last question, I was wondering, when the topology changes due to branch cutoff and expands the feasible region, how do you recalculate the outputs? Oh, good question. So in the optimal transmission switching problem, there's no machine learning here, actually. It was basically just an observation we made. We ran a bunch of these. We noticed how if you remove particular lines, it increases the feasible region in the right direction. And so there's no, that basically results in you just solving the same DCOPF problem again with fewer constraints. So it's quite easy to solve that. So there's no retraining of the model. It's just a heuristic. And then I'll answer this last question, and then that will be my last one. From a deployment perspective, can both traditional approach and proposed approach run in parallel? Meaning we can execute the more optimal operation if we found one and go back to the safe DCOPF and ACOPF post-verification. That's a good idea. I think we probably could run those in parallel. I think the only thing is the price stability that I mentioned before. It's like, if you have prices calculated with ACOPF and then you have prices calculated with DCOPF in the next 5 minutes, that might cause some weird behavior with price responsive assets. Like there were batteries that were responding to real-time price and picking charging and discharging decisions dynamically, and you suddenly change the price in a discrete fashion. That might result in some big changes in output, which basically would possibly result in frequency instabilities. So there would have to be some price buffering or there, but you could run them in parallel. And then, okay, one more question. What are the ACOPF post processes exactly? Okay, so this post processing block, the way that it works right now is it calculates the optimal generator set points. Those are fixed, except for a few generators, which are called slack generators, which are responsible for making up the differences between the physical realizability. So most generators are fixed. In this block, you run an equation solver that takes those generators as fixed. It has a couple variables, which are the tunable generators, and then it adjusts the generation to account for the losses, the reactive power, etc. So same thing here, we fix the same set of generators, and then we run this post-processing with those generators fixed and a few of them flexible, which are gas generators in both cases.
Okay,
that's
thank
all I
you.
got.
You're talking optimizing this by algorithm made me think of, I think, our last week's talk of somewhat of the politics of West Virginia coal, if you will, and how the Public Utility Commission there actually told the utility who schedules their power plants into PJM to actually run the more expensive coal power plants by design. So
Yeah.
there's a non-algorithmic competition, I guess.
Oh yeah, I don't even take
on
into account the social and political objective functions here. But
Right. Well, again, thank you very much. It's been Kyrie Baker, Assistant Professor, University of Colorado Boulder. Thanks for joining us here for the University of Texas Energy Symposium.
yeah, thank you so much. Bye.
Thank you.